Okay, in this video, we derive a marginal distribution of the multivariate normal distribution and see that it's actually a normal distribution again. All right, let's start. First of all, the density function for the normal distribution is this. It's multivariate normal distribution is this. Sigma is the covariance matrix, and its determinant is in the denominator, and exponential of -1/2 x minus mu. Mu is the mean vector, transpose the inverse of the covariance, and this. Okay, but in general, we can always transform x minus mu to x by centralizing. So without losing generality, we can always deal with mu, the mean being equal to 0. Okay, so we only consider the simple case where we consider only x transpose here and x here. Okay, now what we want to do is split this vector. This is n-dimensional vector. So we split this into two parts, x1 and x2, where x1 is a p-dimensional vector and x2 is a q-dimensional vector. And of course, p plus q should be equal to n. Okay, so we split into two vectors and then find the marginal distribution for x1. Okay, that is obtained by integrating this density function, rho of x, over q-dimensional space with respect to x2. Okay, so our job is to find this integral analytically. And for that, we also split the covariance matrix into blocks. Okay, sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. Corresponding to x1 and x2. So sigma 1, 1 is p by p matrix. Sigma 1, 2 is p by q matrix. And sigma 2, 1 is q by p matrix. And sigma 2, 2 is q by q matrix. Okay, but one problem is that we need sigma inverse, right? But sigma inverse is not exactly this. It's not sigma 1, 1 inverse, sigma 1, 2 inverse, and sigma 2, 1 inverse, sigma 2, 2 inverse. This is wrong, okay? But it's a little bit more complicated. Oh, by the way, since covariance matrix is symmetric, we have, this and this are transpose of each other. So sigma 1, 2 is equal to transpose of sigma 2, 1, and vice versa. And next, we want to express sigma inverse in terms of these blocks. But for that, we need some results from linear algebra. And that's what we are going to prove now. Okay, here is theorem 1. Suppose we have a block matrix A, B, C, D, where A is, let's say, n by n, and regular, that means invertible, and B is n by m, and C is m by n, and D is m by m. And in addition, we define another matrix called S, which is defined as D minus C A inverse. A is assumed to be regular, so A inverse exists, and times B. Okay, then if we have these conditions, the inverse of this block matrix is written as A inverse plus A inverse B S inverse. S is this one. Of course, we assume this is regular. And this should be m by m, right? M by m. So S should be the same size as D, which is m by m. and S inverse, and C and A inverse. So this is the first block. And the second block, negative A inverse, B, S inverse, and negative S inverse, C, A inverse. So these are blocks. And the last block is S inverse. Okay, so this is the theorem. So it's not as easy as just A inverse, B inverse, C inverse, and D inverse, but it's a more complicated expression. Anyway, let's prove this. So to prove this, we define a few matrices for convenience. So F is this original matrix A, B, C, D. And W is a new matrix made of the identity block, identity matrix as the first block, and the zero matrix, n by m, and the negative CA inverse here, and identity matrix n by m. Okay, so this is n, m, n, m. So it's the same partition as F. Okay, and another matrix U. That is the identity matrix, n-dimensional, and negative B, S inverse, and zero matrix, m by n, and the identity matrix, m by n, m-dimensional. So n, m, n, m. So again, the same partition sizes. Okay, so first we multiply F and W together, and let's define G as WF. Okay, so W is IO, so I just skip these subscripts, CA inverse and I, and ABCD. Okay, so this is IA, so that's A, and 0C, so that's 0, IB, so that's B, and 0D, so that's 0. And this is negative CA inverse times A, so A inverse and A cancel out, and we have negative C. And this one, this, and plus C. So negative C plus C, so that's 0. And negative CA inverse B plus D. Okay, so this one is defined as this. So D minus CA inverse B. So D minus CA inverse B. So this is S. And next we multiply U and G together, and let's call it H matrix. H is UG. So U is I minus B S inverse 0 I, and A B O S. So this is IAA and minus, oh, that's 0, so it's just A here. And B, and this negative S, S inverse S, so S and S inverse will cancel, and negative B plus B, so that's 0. And this is 0, and this is 0, and 0, and S. Okay. So this is a block diagonal matrix. And what's nice about a block diagonal matrix is that it can be inverted very easily. So H inverse is just inverses of the block diagonal elements. So A inverse and S inverse. So that's it. On the other hand, by the definition of H, so H is UG, but G is equal to WF. So if we invert this, we should have F inverse, W inverse, and U inverse. So from H inverse equal to this, we have, let's see. So F inverse is equal to H inverse. And let's see. First, we multiply U from the right, and then multiply W from the right. Okay, so let's calculate this, and we have A inverse, 0, S inverse, so that's H inverse, right? And U is, what is it? U is this. So I minus BS, S inverse, and 0, and I. And let's leave W as it is for now. So from here we have A inverse 0 and minus A inverse BS inverse and 0, and that's 0 and 0 here, and 0 and S inverse. Okay, now W is I 0 minus CA inverse and I. So let's multiply them. So A inverse and this one, negative A inverse BS inverse times CA inverse. So negative sign here, so it's positive here. And A inverse, that's 0, and negative A inverse BS inverse, 0, and negative S inverse CA inverse, and this one is S inverse. So that's it. That's what we wanted to prove, and we are done. Okay, one more result from linear algebra is about the determinant of this block matrix. So the determinant of this block matrix ABCD can be expressed as this. That is determinant of A multiplied by the determinant of D minus C A inverse B. This is actually S, right? So let's prove this. In the previous proof, we defined this matrix G. Let's see. G was WF. Now, what was W? G is this. W is this matrix, right? And if you look at this matrix, all the diagonal elements are 1s. And this is lower triangular block matrix. So the determinant of this W is actually 1. Okay? So that means if we calculate the determinant of this, that is the determinant of a matrix product is a product of the determinants, right? So this becomes this. And so since this is 1, this is equal to F. So in order to calculate, so this is actually the determinant of F. And to calculate the determinant of F, we need to calculate the determinant of G. Now, what is G? So G was defined as this, okay? And after all, we got this one. Again, this is a block triangular matrix. So that means the determinant of such a block triangular matrix is given by this. So the determinant of A multiplied by determinant of S. Okay, so that's what we get. So the determinant of G is determinant of A times determinant of S, but S is just, by definition, D minus CA inverse B. Okay, so this is equal to the determinant of F. So that's what we wanted, and we are done. Now let's go back to our problem. So we had this covariance matrix split into blocks. Sigma 1, 1, sigma 1, 2. Let's write this sigma 2, 1 as sigma 1, 2 transpose, because that's what it is, due to symmetry. So what is sigma inverse in terms of these block elements. So according to theorem 1, we have the following. So that is sigma 1 1 inverse and plus sigma 1 1 inverse sigma 1 2 S inverse. By the way, S here is defined as sigma 2 2 minus that's C, so it should be what is it? Transpose of 1 2 and sigma 1 1 and sigma 1 inverse and sigma 1 2 here. Okay, so this is S, this S, okay, and sigma, it should be 2 1, so 1 2 transpose and sigma 1 1 inverse and negative sigma 1 1 inverse sigma 1 2 and S inverse and minus S inverse sigma 1 2 transpose and sigma 1 1 inverse, and the last element is S inverse. Okay, so that should be the inverse of this covariance matrix. Now we look at the exponent of the exponential function in the density function. So that is, so exponent is this part. Okay, x transpose sigma inverse x. Okay, so let's consider only this part. So x transpose sigma inverse x. So we split this x into two parts, right? So that it's x1 transpose, x2 transpose. And now we have this, okay, this thing. Let's write it like this for now. So if we expand this, we get the following. So we get x1 transpose this first element, that's sigma 1 1 inverse, sigma 1 1 inverse, sigma 1 2, S inverse, sigma 1 2 transpose, sigma 1 1 inverse, and x1. So this, so 1 1 element, and plus x1 transpose, let's see, this thing. So that's negative sigma 1 1 inverse, sigma 1 2, and S inverse, and times x2. Okay, plus x2 transpose, negative, so transpose of this one, that's S inverse, S1 2 transpose, sigma 1 1 inverse, x1. And the last element should be x2 transpose, S inverse, and x2. Okay, now first let's expand this term. Okay, so we have x1 transpose, sigma 1 1 inverse, x1. And the second one is, let's see, wait a minute, x1 transpose sigma 1 1 inverse, sigma 1 2, S inverse, sigma 1 2 transpose, sigma 1 1 inverse, x1, and negative, let's write it here, negative x1 transpose, sigma 1 1 inverse, sigma 1 2, S inverse, x2. And this one minus x2 transpose, S inverse, sigma 1 2 transpose, sigma 1 1 inverse, x1 plus x2 transpose, S inverse, x2. That's a lot of terms. Now let's leave this first term alone and try to factorize the rest. Okay, so how can we do that? Let's see. So we have x1 transpose, x11 inverse, x11 inverse, x12, S inverse, x12, S inverse. So up to this point, we have a common factor. So let's factorize this one. That becomes x1 transpose sigma 1 1 inverse, sigma 1 2 S inverse. And let's see, let's put x2 first. So negative sign here. And x2 minus this thing. Sigma 1 2 transpose sigma 1 1 inverse x1. Okay, now let's see. We have x2 transpose here, x2 transpose here. So let's, and we have S inverse here, S inverse here. So factorized by x2 transpose and S inverse. Let's put plus sign here. So then we have x2 from here minus this thing. Sigma 1 2 transpose sigma, wait a minute, this should be sigma, and sigma 1 1 inverse and x1. Now we have this and this as common factor. So let's factorize it. And okay, so if we factorize this, we have x2 transpose minus this thing. So that would be x2 minus, let's see. So if we transpose everything here, it should be sigma 1 2 transpose, sigma 1 1 inverse. By the way, sigma 1 1 should be symmetric, so it's transposes itself. And x1. Everything transpose, and this factor, S inverse, x2 1 2 transpose 1 1 inverse x1. So we have the same vector here and here. Okay, let's put this as a square and this as a circle. Okay, so if we have this exponential, negative 1 over 2 square and negative 2 circle. Now, this matrix is S inverse. So if we integrate this over x2, okay, so this term doesn't contain x2, so it will be just a constant. And this one, if we integrate this, what we get is this exponential of negative 1 over 2 square. So that's this part. And from here, if we integrate it, we should get square root of, what is it? 2 pi, since it's q dimensional, 2 pi to the power of q, and the determinant of S. So let's put this back to the original density function. So if we integrate the original density function for the multivariate normal distribution and integrate with respect to x2, then what we get is the original normalization constant is 2 pi to the power of n times the determinant of sigma. And from here, we have exponential of negative 1 over 2 x1 transpose sigma 1 1 inverse x1 times this thing, okay, times 2 pi to the power of q and the determinant of S. Now, using theorem 2, the determinant of sigma is the determinant of this block matrix. 1 2 transpose 2 2, and according to the theorem 2, this should be equal to the product of this and what is it? I don't remember. So that should be this d minus CA inverse B. So that should be So actually it's S, right? So substitute this into here. So we get this constant term should be 1 over square root of 2 pi. So n minus q is p to the power of p, and we have sigma over s. S over sigma is 1 over sigma 1 1. So here we have sigma 1 1 determinant and exponential of 1 over 2 x1 transpose sigma 1 1 inverse and x1. So this is again a normal distribution, the density function for the normal distribution, where this covariance matrix sigma 1 1 is obtained by just ignoring all the parts that involve any contribution from elements of x2 vector. So we only take this one and put this one here. We get the marginal density function for the normal distribution. Okay, that's it. See you later.